Hi everyone. Today I'll talk about weather forecasting, and this is the last lecture video before we have exam 2 on Wednesday. And just to remind you once again that all the materials that you need to prepare well for exam 2 have already been posted, and the exam 2 will also be very similar in format, not in content. It will be in format very similar to exam 1, but of course this time we'll only cover the last 5 or 6 lectures we have covered after you had the first exam, right? So there will be 40 multiple choice questions again, and it will be very quite similar to the some of the questions that are posted on iCollege in the study guides. So I would encourage you to go all the materials posted on iCollege, including the extra readings, right? Some of the topics they have already covered the last 2 weeks or so are not not included in sufficient detail in the textbook. So I've added extra readings so that it's just a page or two that you can read to prepare well for the exam, right? Before I start talking about weather forecasting, I just would like to remind you again. So last lecture we talked about air masses and fronts, remember, and there are four main types of air masses, so including maritime tropical, maritime polar, continental Arctic, continental polar, and maritime and continental tropical, which is not showing here. So even if like the four are very dominant, we do have in some places, especially in places like Arizona and Tucson, and in Arizona and New Mexico, we do have the continental tropical air mass is much more prevalent throughout the year. So the differences when we're looking at the air masses, of course, if you may be able to recall, as we're looking at changes in temperature and specific humidity, and then looking at where the air masses are coming from. So if they're coming from from the ocean, they would have a maritime in their name, and if they are from the continental, so if they are from continental, usually these are dry air masses, and then they will have continental in their name, right? Right. So now to weathering, weather forecasting, and so before I start talking about going into weather forecasting in more detail, so there are three important pieces that I would like you to know. For instance, when we're talking about the acquisition of weather information is also a very important piece of weather forecasting, right? So there are organizations that we rely on for weather information. For in the U.S., for instance, this is the National Center for Environmental Prediction, but generally globally, and then we also have this information really available in the if you look at the World Meteorological Organization website, right? So there are 3 different categories or branches of the acquisition of weather information, the processes, right? So we do have what we call watches and warnings and advisories, right? So when the watches, these watches are issued by the relevant authority. In this case, for instance, in the U.S., that is the National Center for Environmental Prediction. So while these are typically favorably conditioned for the potential hazards, right, for hazardous weather, there are those initial conditions are satisfied, and then of course when these watches are issued, then the citizens are expected to pay attention, right? But no more action at this stage. There is no need to take action or freak out, right? But we do have, when we have this warnings issue, that's when we need to take action, right? So that means when warnings are issued by the relevant authorities, so that means hazardous weather is imminent, right? So, or it's actually occurring in the nearby places, right? So, for instance, these warnings will be issued, for instance, if we have a very, very powerful thunderstorm approaching Atlanta, right? So then, in this case, then the citizens are expected to take action. But what you need to remember is even if these warnings are issued initially, of course, given the chaotic nature of weather, these issues are always constantly being updated, right? So advisories, for instance, these are warnings, but usually we're dealing with less hazardous weather than we have in typical cases when warnings are issued by relevant authorities, right? And then the internet, especially today nowadays, plays a crucial role in these global communication efforts. So. If you look at, for instance, this is quite old, but it really still applies, and this is from Hong Kong, but it really, it's probably, it's most likely the same in many places and cities, big cities in both hemispheres. So in the old days, of course, we relied more and more television, radio, and even in some cases like newspaper journals, newspaper and journal are chapters in newspapers to get that information, right? Especially, I believe in some of the newspapers we have do cover weather on a day-to-day basis, but nowadays we are more reliant on our smartphones, right? So this information is easily accessible, right? Whether we have when warnings are issued or advisories, so we'd be able to capture that information in our smartphones, and this information is quite accessible, right? And then when we were talking about weather forecasting in general, right? So there are different tools we utilize, right? So, so for instance, especially this today. So we have increased capabilities, right? Given owing to the technological advancements. So our weather forecasting systems, they process satellite data, radar data, surface observation, and then of course data even from this weather balloons, right? And so even the weather forecasting model output, right? So we have this complex models. What we call this weather forecasting models is they represent the atmospheric conditions at any given time, and then we can use those data to refine our forecasts, right? So there is a lot of information that's already available, right? So before I jump into the different types of methods and processes we utilize in weather forecasting, just want you to show this interesting graph here, right? So for instance, when we have this weather balloon data, quite different from the data we get from stations, right? The different stations. What we have is we can actually capture the vertical atmospheric profile of a place or a site or a point in space, right? So what we do have, for instance, I ask you this question: is there fog based on the sounding data here, right? Is there a likelihood of fog formation? And the answer to this is yes. Remember in previous lecture when we talked about dew point and air temperature, the dew point is the temperature at which condensation occurs, right? So when the dew point is well aligned with air temperature, that means the dew point temperature is exactly the same as the air temperature, and then you should be able to expect fog formation, right? Remember, fog is a form of condensation. So if we have cases like this in Atlanta, then we do have foggy days and fog formation. So we can look at this vertical profile from weather balloon data, for instance, and then we can see why it is foggy in that day or why we have clearer sky, right? But when we're talking about broadly, when we're talking about weather forecasting, we are more and more relying on what we call the supercomputers, right? The need to have these powerful computers is that we actually have a lot of data. We're able to acquire a large data sets, like from satellites covering large regions. And then in order to make a weather forecasting, we need to process all this information in a timely manner, right? So we can't do this manually, otherwise it would take us a very, very long time. So we can process all this information and generate forecasts in a very timely manner, right? And we're more and more for weather forecasting, where of course we are more and more relying on satellite data. And then there are specifically two important types of satellites we use in weather forecasting. One, we call them geostationary satellites, and the other is a polar orbiting satellite, right? Why we need the polar orbiting satellite is the geostationary satellites, they are situated some 36,000 kilometers above the equator, right? And then they are at a fixed location, right? And then they can only, in a sense, they are only overhead over the tropics, and then they're not able to cover the polar regions, right? To cover the polar regions, and then we need those polar orbiting satellites. But in weather forecasting, of course, we're integrating both the data from the polar orbiting satellites and the geostationary satellites, right? Remember, if you live in places like in Atlanta, for instance, where we do have the influence, the cold air intrusion during the winter seasons, and then while during the summer season, we are actually, the weather patterns are dominated by the maritime tropical air mass coming from the Gulf and the tropical regions. And we do need this both we use the polar orbiting satellite and the geostationary satellite to generate accurate forecasts, right? But when we're talking about satellites, they do work differently, right? And we're not actually measuring the exact variables. And for instance, the satellites, they don't have the thermometers to measure temperature, right? One, it wouldn't work. One, they are actually located some 36,000 kilometers above the surface, right? Above the equator, right? If you're looking at the geostationary satellite. So even if we have thermometers installed in these satellites, they wouldn't be able to capture to tell us anything about the temperature, the lower atmospheric temperature, let's say, for instance, over Atlanta, right? But what they do is they actually measure the infrared energy that's being released, being reflected to space by different clouds we have, right? For instance, if you have what we call this high clouds, like cirrus clouds, they appear much whiter, while the low clouds, they tend to appear, they are much darker. And then it is these images that we convert to the relevant variable, right? So there is a complex calculations involved to converting this data, these images we have, right? And to calculate temperatures, precipitation, and other variables that we are interested in. And So remember, so the weather satellite, what they are detecting is heat energy that's released in the form of infrared radiation, right? And so remember, the infrared energy is invisible to the human eye, right? And so what you have is, it would look like something like this, but like with more complex models and complex satellites, we are indeed able to actually even reconstruct, to generate this 3D reconstruction of different parameters. So for instance, here, different variables. So for instance, here you're looking at, for instance, precipitation data, right? So we're able to convert these images and then look at, generate these images and then convert them to quantities of known variables, whether it is temperature, precipitation, or other cloud properties, right? So and then when we're talking about the computer and weather forecasting, of course, there are different key steps that we need to understand, right? There is the analysis, and then of course, there is the numerical weather prediction, and then there is like the atmospheric models, and then what we call the prognostic chart for weather forecast for a specific future period, right? Whether we're looking at hourly change or daily change. But when we're looking at, sorry about that. When we're looking at these different pieces of weather forecasting, so for instance, for analysis, we rely on what's the data at present, right? To really, and then we do have different models, different computer models with different resolutions. And then we're always comparing the analysis with the model data outputs, right? As I'll show you in the next slide. So here, what you see here is, in this graph, we're comparing different models, right? One here, what you see, the WRF model, it's like it has a 12-kilometer resolution. No, well, it's like a much higher resolution than what you see here. The model, the GFS model, it's a 60 kilometers resolution, right? But even if like the resolution is quite different, then they actually reproduce what you see here, the low pressure zone of the coast of the west coast here, right? They're quite similar. So what this tells you is that, okay, then comparing to the analysis. So this is the reality at present, right? So they do represent the low pressure zones quite well, right? There are some differences, of course, you see here and here, especially while the high pressure zone here is like quite well represented compared to the relatively low resolution model you see here on your right. So, but the idea is that we do have this different models we use for weather forecasting, right? Different computer models, and then we test them against the analysis. So which one is better, right? The question is, which one is better to represent a characteristic, a situation that's present, for instance, over the ocean, while if you're like looking at, for instance, over Atlanta, right? You need the more high resolution models, because we do have complex subgrid processes taking place usually in Atlanta, right? It is really very complex situation that we have in Atlanta because of where Atlanta is located. It can be potentially impacted with complex different air masses coming from different regions, right? And so, but sometimes this what we call the weather forecasts are quite inaccurate, right? They can be inaccurate. So one of the most important reasons is weather by default, it's a chaotic system, right? And it is actually highly sensitive to our ability to observe the weather, right? And then it's impossible, it's quite impossible because we can't really follow what's happening at the same time, we can't follow what's happening at all places at once, right? And that means the initial conditions are always changing, right? So I don't know if you have checked the weather forecast for this week already, but I was checking the weather forecast on Saturday, and then it was expected to be, it was forecasted to be a cloudy day today, right? It was supposed to be cloudy day based on the forecasts that we had on Saturday, but it's really a sunny day today, right? So it shows you that, it's a chaotic system. The initial conditions are changing in minutes, hours, right? So it's very, very difficult. It's actually, that's one of the reasons that, weather forecasts are always they're not going to be 100% accurate at all times, right? And then the other is grid spacing and incomplete data coverage. Of course, the different types of model data we have, they do have, even if, for instance, some of the highest resolution models we have, they do have this 12 kilometers resolution, which is still deficient and then unable to resolve what we call this subgrid processes and cloud formation and land surface processes, right? And because of that, of course, from time to time, the forecasts we get are not exactly aligned to observations, right? But incredibly, our forecasts are incredibly being accurate, right? Especially the very short range forecasts, and then what we call these three: the short range, very short range, medium range forecasts. They are incredibly they are more and more accurate. While the long range forecasts, that's when the forecast starts more and more to divert from observation. Again, it's a very chaotic system, so we can't really accurately forecast the weather 2 weeks or 3 weeks ahead, right? And then of course, when we're looking at what's going to happen next season, these are outlooks, right? We are now looking at more broad scale processes to have this monthly and seasonal outlooks, but we can't really have accurate forecasts going beyond the 2 weeks, right? And there are different types of forecasting methods. For instance, what we call persistence forecast and trend forecast is that, if it is sunny today and it's going to be sunny tomorrow, right? We look at those trends and then we actually can make a reasonable prediction for what's going to happen in the next day, in the following days, right? And then in a way, the analog method is also quite similar. What we do in the analog method is for instance, that's March 8th. We can go the first week of March. We can go back last year or the year before, and then see how the weather was like, right? So for analog method, it's more dependent on the history, right? So the chart in history could be we're looking at the typical seasonal patterns, or we look at the previous days, the last weeks, and based on that, based on persistence and then the analog method, we can actually make a forecast. And the other one is statistical and probability forecast. Of course, based on the initial conditions we have, then we can actually calculate the probability and based on that make a forecast, right? And the other one is what we call the climatological forecast, and then we use the climatology to predict future. And so, for instance, if we understand the climatology very well, and it's very predictable. For Tucson in Arizona, for instance, it's quite predictable. The climatology is quite predictable. They get it's very dry region throughout the year, and then it's an important sink region for the North American monsoon. And then once the climatology is very well understood, then we can actually use that information to predict the future, right? But again, for this is a different flow from places to places, right? So in Atlanta, it's much more complex. So we rely on this sophisticated weather models to make accurate prediction, right? Okay. So you see this descriptions quite frequently, I believe. So for instance, you get this sometimes chance of rain is 60% for one area, right? In Atlanta, for instance, you may get like a chance of rain today is 60% for Atlanta, right? What this means is that it doesn't mean that like it will rain over 60% of the area, but what we're trying to say is, what the forecast is trying to say is, there is actually a 60% of chance that any random location in the area will receive a measurable rainfall, right? So it's not exactly about that particular spot, right? So when this forecasts are generated, then, well, it is going to be rainy, well, but for instance, even if we have a box in Atlanta, so it doesn't, it may be in Decatur or in downtown Atlanta or Midtown, but like the idea is like there is a chance of a 60% chance that any random location within the area would receive a measurable rainfall, right? So when someone claims that, well, the forecast of a 50% chance of rainfall is like tossing a coin, well, that's actually not the case. We do know that if the initial conditions are satisfied, we do know that it's going to rain, right? But it's just it's likely that it's at any random location within that box that we're looking at, right? Okay, so the accuracy and skill in forecasting, like I said, it also depends on several things, right? Of course, the models, the resolution of the models, whether they are able to capture these complex processes that take place in a very, very, very limited space, right? Also, then the chaotic nature of the weather by default, right? But the forecasts show skill only when they are more accurate, right? So for instance, sometimes persistence and climatology are surprisingly accurate, right? And then especially if you understand the climatology of the region, right? So you look at the data, and then if it is like a desert, right? So you look at the data, well, okay, it's like, and then you're not expecting precipitation, just looking at what happened the past days, weeks, and then understand the climatology. You can make an accurate forecast, right? It works sometimes, right? But it doesn't really necessarily mean that, like, your forecasts have skill, right? Especially this works in places like in Atlanta, for instance. Like, you can actually sometimes, just looking at persistence, what has happened in the previous days, and the climatology of the region, understand the climatology, the seasonal climatology of Atlanta, you can actually make a pretty good forecast for the next days. But it doesn't necessarily mean like it's always going to be accurate. So it doesn't necessarily mean that your forecasts have skill, right? And then remember, we don't really have forecasting skills in predicting the weather 2 weeks in advance or 3 weeks in advance, right? That's the maximum that we can go. 2 weeks is the maximum. So usually, even with this long range forecasts, you typically stick with the day, right? Whether it's going to be cloudy or sunny day or. But we won't be able to actually, forecast for what's going to happen at 2 a.m. or 2 p.m. Or at noon at a particular day 2 weeks in advance, right? And but before I end today's lecture, just want you to remind you again, for instance, of course, if we're looking at forecasts, right, we are relying on the different types of data, right? Surface pressure is very important. Temperature is very important, right? So if you look at this pressure map for the U.S. and you see, you'd be able to see that there is a clear difference between the West Coast and the East Coast. We do have, in this particular case, a low pressure zone situated here in the East Coast, right? So if you look at the temperature, of course, temperature is also directly related, inversely related to pressure, right? When we have a change in temperature, we also have a change in precipitation, right? So if you look at this is where we have the low pressure zone, right? And if you look at the temperature, this is also where we have warm air, right? And then we can also look at whether, like, we do have, if we have gradients, right? So we have large gradients. For instance, we have 1016 millibar here. It is 1008 millibar here. In the East Coast, right, in this low pressure zone. So we do have a large elongated air of a front, right? So we can draw and make inferences and then draw these front lines, right? Because these front maps, we talked about fronts in the last lecture. So the fronts are the boundary where we have the cold air and the warm air meet, right? So if we do have the temperature and the pressure, then we can actually easily draw this front maps based on manually. Like we can actually calculate those the frontal areas. We can draw frontal maps, right? That would be it for today. Again, I would encourage you to go through the extra reading, particularly relevant for weather forecasting, which is not actually covered in the textbook, right? And for Monday again, on Wednesday, you'll have your for 40 questions, you'll have 75 minutes allocated, and then you'll have the exam 2 will be available for 24 hours. But if you're busy and then if you're not available during that time, please let me know, and I'll try to make the exam available longer than 24 hours, right? And good luck with exam 2. I'll please check your iCollege, and I'll post more information tomorrow. Re the exam 2, and in terms of what it contains and then how many questions, and I'll repeat that I'll also post that in the announcement page, right? Good luck.